even with a blend of gray hydrogen and blue hydrogen, the carbon footprint of the data center is lower than any connection to any grid in the United States.
Hello and welcome to Perspectives with Nilo, a regular podcast bringing you news and views from around the world. I'm your host, Nilo Sullivan. If this is your first time listening to our podcast, you might also like to explore our more than 40 past episodes on topics ranging from technology to politics and sport. And you can find them at pwnilo.com or wherever you get your podcasts. And don't forget to leave a like or subscribe. In today's digital age, data centres have become the backbone of our interconnected world. From streaming our favourite shows to conducting complex financial transactions, these high-powered facilities are the engines driving our digital revolution. But as our reliance on technology grows, so does the energy consumption of these data centres. This increasing energy consumption is driving data centre operators and tech entrepreneurs to explore new ways to power these energy-hungry facilities more efficiently and sustainably. In this episode, we talk to Yuval Bachar, founder and CEO of Edge Cloud Link. Yuval and his team are pioneering the development of off-grid sustainable hydrogen-powered data centres, and they've created a proof-of-concept colocation site in Mountain View, California. As we heard in our previous episode from the Open Compute Global Summit in San Jose, data centres consume large amounts of electricity. And this increasing trend is being driven by new technologies such as artificial intelligence and machine learning. According to a recent report from the International Energy Agency, there are currently more than 8,000 data centres globally. And in 2022, they are estimated to have consumed around 460 terawatt hours of electricity, about 2% of global demand. And they predict that this demand could double before the end of the decade. While it's still early days for AI and ML, the emerging capabilities and potential benefits have created an urgency for tech companies to continue to innovate in this important global race. From a sustainability perspective, many data center owners and operators have also committed to achieving net zero emissions by 2030. So the increasing electricity demands of AI and ML place an additional urgency on achieving a successful transition to sustainable power sources. In 2023, renewable energy sources accounted for an average of 30% of the world's electricity supply. And as many national power grids also face demand constraints, data center operators are looking to off-grid sources for alternatives. One option for data centers is to generate and store power on-site with solar or wind turbines, plus battery storage. However, given the space requirements of solar and wind, this may not always be feasible, and many operators resort to purchasing renewable energy offsets in the form of renewable energy certificates or power purchase agreements. More recently, we've seen announcements, particularly from hyperscalers, of power purchase agreements for nuclear power, but also their intent to investigate small modular reactors, or SMRs, and nuclear fuel strategy roadmaps. However, many commentators agree that the construction timeline for small modular reactors is likely to stretch to the end of the decade before they break ground. A third less controversial option is the hydrogen-powered data centre. While some data centre providers have deployed hydrogen fuel cells as backup power supplies and others are conducting trials, Edge Cloud Link, or ECL, based in Mountain View, California, has combined fuel cells using green hydrogen derived from renewable energy with battery energy storage and a highly reliable power architecture to deliver an off-grid, sustainably powered data centre. ECL say their mission is to deliver a fully sustainable green data centre to market via disruptive engineering, design and deployment of emerging technologies that have never been combined. They claim that the resulting efficiency culminates in a lower-cost alternative with zero carbon emissions. We went along to chat with the founder and CEO of ECL, Yuval Bachar, and I began by asking him what the focus and vision of ECL is all about.
So ECL was established with three main goals. One is to deliver a fully sustainable zero emission, zero water site that can be operating at high performance, and as a result can be actually operating off-grid or on-grid, depends on what you have as availability of grid. So sustainability was key for us. And the second aspect is to create a very efficient data center. Today, data centers are averaging about 60% overhead. We had a target of less than 10% overhead on the data center. And lastly, to develop a platform that can be consumed by everybody, not just by the hyperscalers. For a very long time, the data centers of high performance and high availability and large scale were only built by 4 companies, which are the hyperscalers. And the rest of the world had to operate in colocations, which are inferior by far from any data center by hyperscalers. We wanted to bring the capabilities that we see at hyperscalers data centers on a smaller modular solution. For that, we actually established a company, and we started by building the data centers in a reverse way than traditional data centers. Traditional data centers build buildings and actually occupy them with IT. We looked at the problem from engineering perspective and say, okay, what is the best way to engineer the best data center? And then we engineered every aspect of it, if it's the power system, if it's the cooling system, the management system, and everything around it. And then, okay, so now let's take a look and see how we put it in a building. And we put it in a building which is much more efficient than traditional data center. And as a result, we can deliver a platform which is highly competitive in the market, but very high performance and high end in the demand of what we're seeing right now for AI.
I suppose one of the things that catches people's attention a lot about your design and your solution is you say it's the greenest data center solution in the industry. Tell us a little bit more about why you can say that, what the features are and the technology behind it.
Yeah, so we started with how do we actually make the most sustainable data center? And we started working about understanding what's the carbon footprint that comes with connection to the grid. And we found out that the grid is actually, in most places in the world, it's actually extremely contaminating the air because it comes with a very heavy carbon footprint in the generation. If it's made of coal, natural gas, and other fuels which generate most of the grids in the United States and in Europe. I think the only special country is France, which actually have very, very large set of nuclear plants, so they're not burning a lot of fuel. So that was the first thing, and because of that conclusion, we decided to go off-grid. So we're not connected to the grid at all. So we run our data centers on a microgrid, and when we generate energy on site itself. We deliver it with zero loss into the data center because the power generation system is 10 feet away from the data center. Now we had to go and see, okay, how do we actually generate energy in a reliable way, because the data center have very stringent requirements for 24/7 and very high availability. So it's not simple to create a stationary power generation system which will be clean. We looked at all the aspects, natural gas, wind, solar, and everything else that you can fit. And our conclusion was that the best solution to create energy in a clean way was leverage hydrogen as our fuel and run fuel cell system to actually generate the energy from the hydrogen. And what we found out also that the byproduct when you actually do that is water. So we got to the point that actually the water is not required for the site as well. We produce our own water that we use in the data center. That was the first step to actually create a first stationary hydrogen-based fuel cells power generation at the scale and at the availability that's required from data center. The second level to actually make the data center as green as possible is efficiency. Because if we actually produce higher power than what we actually need for the IT, this is lost power from our perspective. It doesn't give us any value from an application or utilization of the IT. So we put a target to actually create a very, very efficient data center, and we created a data center which has an overhead of 6%, which means PUE 1.06, compared to traditional average in the United States today. Data centers have a 60% overhead, which means PUE of 1.6. And PUE has been abused recently to all kind of directions, but if you look at the pure definition of PUE, is the total power of the data center divided by the IT power, without credits, without anything around it. And that's what we did. So we were able to do a very efficient data center as well. The third thing was a lot of data centers today are actually using UPS system and diesel generators as backup in case they lose the main primary source. And we decided that we have to eliminate the diesel generators because diesel generators is a contributor to the carbon footprint of the site, and we want to be zero carbon footprint on the site. So we eliminated those units by changing the power architecture. We moved to a multi-active sources of energy. One of them is a hydrogen generator. The second one is a high-capacity battery that we actually feed in an active mode, not as a backup mode. And we have two more options to feed external power. It can be solar, it can be wind, it can be grid if the grid is available. And then we deliver a system through our power conditioning system. We deliver a power into the data center, which can be AC or DC. That is eliminated the last element in data centers, which is a contaminating element, and that's the diesel generator. With that, we're able to achieve the zero carbon that we looked for without buying credits, without doing any offsets.
And I've heard you talk about the 1 megawatt building block that you use. So if I can ask you, is this targeted at colos, at larger installations, at hyperscalers, or all the above?
So this is targeted for a modular block that can actually be repeated into large data centers. Yeah. And what does that mean? And why modular blocks? So a modular block helps us deliver the system to operate in a most efficient way, both from a cost as well as operation, power, and cooling. And then we just repeat it and actually put more and more of them. We just announced a 1 gigawatt site, which means 1,000 blocks of 1 megawatt, which are going to be put together. Now, what's the added advantage of actually creating the modularity? So our data center cycles today is between 3 to 4 years to build. So when somebody decides I'm going to build a data center, put the plans in place, it takes 3 to 4 years. Our cycle for AI technology right now is 9 to 12 months. Every 9 to 12 months, we have a new generation. So if we decide to build a data center today and take us 4 years, we're going to go through at least 3 or 4 cycles of AI chips and systems, etc. The chances of us actually hitting exactly what's going to be required in 4 years is very, very low. We have to guess, basically. What we did with modularity is we build phases of 6 months. So every 6 months, we build about 100 to 150 megawatt of data center. And every 6 months, we can change the block. So we can change the module to actually be different, to accommodate and track the technology development, which traditional data centers could not do.
And so you mentioned AI there and the growth of AI, and one of the things we see is the increased power consumption of the latest AI chips. Can your design facilitate direct liquid cooling, for example, of these chips, and cool the compute hardware if required, in terms of the trend that we see?
Yes. So our data center was designed from day one to actually deliver 75 kW per rack. And it's targeted for high-density GPU systems, which are not direct on chip. A typical DGX system today with the H100 to H200 is actually between 8 and 14 kilowatts per system, and we can put 4 or 5 of them in a rack. That fits today's technology. What we expect to see in 2025 is racks which require a combination of direct on chip and air cooling, and that will hit the 135 to 145 kW per rack. Our next generation delivery of our blocks will include that capability per rack of 135 to 45 on the combination of the two. We have a unique design that we plan to actually introduce in the next GTC that will actually show how we deliver a combination of air and direct on chip at these levels to accommodate the next generation of AI.
Okay. Just to stay with the hydrogen power source for a little bit, is it true to say that this approach is only 100% green or sustainable if green hydrogen is used, which means hydrogen is produced by electrolysis using electricity from solar or wind, for example, and then the hydrogen is compressed, transported, and converted back to electricity to power the data center. This is the cycle. So I guess my question is, how efficient is that process, converting from electricity to hydrogen and then from hydrogen back to electricity again?
Yeah, so there are multiple aspects that we need to address with that question. First is, do we have to actually produce green hydrogen to actually justify a hydrogen-based data centers? And the answer is no. And we did a full analysis on it, and we showed that even with a blend of gray hydrogen and blue hydrogen, the carbon footprint of the data center is lower than any connection to any grid in the United States, which is pretty incredible that we can actually take existing materials which already exist and we don't have to reinvent them through green processes, etc., and still be much, much better, significantly better than any grid in the United States. Now, we definitely strive to get as much as possible green hydrogen. The problem with that is that the volume of hydrogen that we need to sustain data centers which are zero emission, zero water, fully sustainable, is too high compared to the available green hydrogen production in the United States. And green hydrogen production in the United States is growing, and green hydrogen production in other places is also growing very fast. But our pace of growing the data center is much, much faster. So we decided consciously that we build the data center which is zero emission, does not have anything coming out of it, and then we will feed it with the hydrogen which is available for us, depending where we are. If we have the ability to get and source 100% green hydrogen, the answer is yes, we're going to take it. If we do not have it, we'll take a blend of gray and blue, which gives us still much better carbon footprint than a grid connection. Now, if we talk about the efficiency, you asked about efficiency of green, does it make sense to actually do solar to hydrogen to electricity back into the data center? The problem with solar and wind is these are technologies which are unreliable power. So they deliver power which today is there, tomorrow is not there. With solar specifically, the sun is out for about 8 hours, or on a good day, and sometimes it depends how north you are, probably 6 hours. And then you have to backfill the rest of the hours with energy because data centers operate 24/7, 365. They don't have a downtime, uptime. They don't have a activity time, no activity. They always work. So we need to be able to figure out how to store energy for the remaining of the hours. There are two main ways to store energy today. One is batteries that a lot of people use in a utility level. But these batteries do not scale to the level that what's the requirement is coming from the hydrogen, from the data centers. Hydrogen is an alternative to batteries, and not only an alternative to batteries, it's actually batteries on wheels. So because you can move the hydrogen from one place to another, you cannot move the battery from one place to another. So if you have a dependency on the grid connection, then the batteries will only give you so far, take you so far with that. Plus, you create a dependency on something that people don't look necessarily at all the time, and that's the transmission side. It's not the generation only. Yes. The transmission is a challenge as well right now on the grid. And even if you have battery to store the energy in, theoretically, then you don't have the transmission in a lot of places. I think Ashburn, Virginia, with Dominion is the biggest example. Dominion just cannot deliver the power. Even if they have the power, they cannot be delivered. So storage with batteries will not help you because it feeds through the same transmission line. Producing hydrogen and then moving it through a pipeline or moving it through a delivery system is the solution that gives you the ability to have the full freedom to put the data center where you want it. And it can give you the ability to create data centers which is at the level of availability expected by data centers. Our data centers at ECL are 6 nines in availability. So they are 99.9999% uptime, which means no downtime, basically. And we can achieve that because we can get delivery of hydrogen and we don't have a dependency on the grid. And I'll give you an example in our area. Our first data center is here in Mountain View. And in Northern California, we constantly get blackouts and brownouts on different times, events that happen. If you do not have ability to actually get off-grid backup system, you will actually have to resort into diesel generators. So your data center immediately becomes non-sustainable. If you have an on-site hydrogen that you brought in liquid state or in gas, then you actually don't have a dependency on that anymore. And then you can continue to operate 24/7, 365 reliably.
So hydrogen is a good storage mechanism. Yeah. And I noticed that the Biden administration here in the US has produced a hydrogen roadmap, a national hydrogen roadmap to help greater adoption of hydrogen and to help drive decarbonization goals. But reviewing the roadmap, it seems like it's a massive undertaking. Where not only hydrogen production has to happen, but also storage and distribution infrastructure needs to be built. Are we still in the early days of what will be a very substantial effort, do you think? And how long do you think this will take to get traction? What's your current kind of insight on that?
So I think so the IRA that has been put in place 2 years ago was trying
Inflation Reduction Act.
Yes, it was trying to actually deliver an incentive to create a hydrogen economy, and it gave incentives for producing hydrogen, gave incentives to actually use hydrogen, and all kinds of things around that. I personally think that there is enough business justification to actually create the hydrogen even without intervention of the government. And we're proving it in our data center. Today, we can build very large data centers from ECL because we don't depend on the power grid, because right now highly restricted almost everywhere. We can get the hydrogen because there is enough hydrogen out there. There are thousands of tons per day of hydrogen can be delivered. And our consumption of hydrogen as a large off-taker, enabling our providers to invest and build more systems that generate hydrogen, green, blue, and gray, and deliver them through a pipeline system. In my view, building a pipeline system is critical for our economy if we want to actually make an economy that can actually rely on hydrogen. And it's not just data centers, it's a lot of other aspects of delivery of hydrogen through pipeline. If we don't deliver through pipeline, the challenge we have, it's expensive to liquefy the hydrogen and then put it on a truck and deliver it. And that slows down the adoption of this technology. And I think, in my view, the IRA is great and it helps us, but we have a business justification even without the IRA to create this new economy of hydrogen. And I think Europe took an approach around this and saying, yes, we believe we need to create a hydrogen-based economy and we'll invest in it.
A lot of governments have given commitments to meet certain climate goals by 2030 or 2050. Do you think they will maybe incentivize their more carbon-intensive industries to use hydrogen rather than data centers, for example? And do you think that will affect data center adoption of hydrogen?
Yeah, I think clearly they will try and reduce the carbon where it's actually heavily used. But first of all, data centers are going to be a significant contributor to green gas emission because the growth in data centers right now is exponential based on AI. With that, will that slow down it for data centers? I don't think so. I think what will happen is that we're going to see more and more production, more and more availability of pipelines and delivery systems. And it's going to be one big environment where if you can use hydrogen as a source of energy, then you can do that. A lot of the areas that actually need to be decarbonized and using other materials are not using necessarily this for power. They're using it for other aspects, and hydrogen is not necessarily a replacement for those. So I think hydrogen as a fuel and a mobile fuel that we can move from one place to another is here to stay. And we are representing a segment which is consuming a lot of energy. And when you consume a lot of energy, you want to actually minimize your carbon footprint. So there will be a place, and there will be actually a strong place. We see that based on the engagement that we have with our suppliers of hydrogen. They were looking for a very long time of to who is the off-taker is going to take my hydrogen. And suddenly we came and said, we build data centers, and we need very large quantities of hydrogen to deliver very large data centers. And they basically say, okay, this is exactly what we were looking for. So if there will be adjacent markets, great. More demand, lower cost.
Earlier you touched on the non-green varieties of hydrogen. So some of the critics of these say that things like blue hydrogen, for example, where fossil fuels with carbon capture and storage is the method employed. They say that like this has a worse carbon footprint than if you burn natural gas for fuel instead. I think they're also critical of grey hydrogen and so on. What's your kind of position? What's your answer to these people who kind of are saying, this is just more damage to the environment. It's not making things better.
So I think if you look at it's very simple to measure it, and we need to measure it by numbers, right? So the numbers speak for themselves. Is every color that comes with hydrogen comes with a carbon intensity associated with it. And blue, for example, comes with under 3 kilograms per kilowatt hour, something like that. And when you do that calculation, you have to compare it to what's the alternative, right? So the alternative is actually getting power not from that, but getting power directly, or generating energy with natural gas directly. The challenge that you have when you look at generating energy with natural gas, which is possible to do directly, is that you bring the problem all the way to the end point. So the data center right now is not capable of actually transitioning into a green energy environment, even if the hydrogen will be green, because it's built to actually take natural gas. When we try to solve a problem at that scale, which is decarbonizing the data centers, it cannot be fixed in one step. The one step that we did, a huge step, is saying once you enter the data center, there's nothing coming out of the data center. There's zero emission. Now let's go and fix the source of the energy. Now, if you look at the blue hydrogen carbon footprint and you compare it to the grid, in the US, the blue carbon footprint is better than any grid in the United States. So if you take how much carbon is associated with the grid in the United States per kilowatt hour, and you compare it to our generation that we do with blue hydrogen, we're by far better, almost 2x better than any grid in the United States. That's a good big first step. Now, the next step is actually to make it more efficient, is to create other types of hydrogens, to enable more green hydrogen production, to find gold hydrogen or blue or white hydrogen, or to do pink hydrogen from nuclear plants, whatever the solution is. But we solve the problem from the fence of the data center in, there's nothing there. Now let's bring into the fence the best hydrogen we can.
But I guess you're also talking about that chicken and egg situation. If you never start because you never have the supply of hydrogen, nothing's going to happen. Whereas creating the demand for it, at least you're moving in the right direction, and more green hydrogen can be created later on. At least now you will have the demand for that because you've created the end user, as it were.
You are absolutely right. So the generators of hydrogen until now were generating hydrogen for mostly for the refinery operations, and they were looking for a very long time is who is my off-taker, and we came in and basically said we're going to be a large off-taker, almost just as big as the refineries when we actually at full scale, and we actually have a motivation which is completely different than the refineries. We're trying to actually decarbonize the world. Now we gave them a justification to go and make investment and creating greener and greener and lower carbon footprint into their supply of hydrogen, and justify the investment because they will have a return, because we are a long-term customer. We are a long-term off-taker because our customers, which are leasing the space of data centers, are long-term customers. They're 10 to 20 years. So if you have a 20 to 20 years agreements to off-take the hydrogen, it justifies for them to invest the millions of dollars they need and the years of building up more and more blue, green, and whatever color that will be lowering our carbon footprint. So our goal is to get to the point, of course, that we want 100% green. But if you look realistically, today, for the volumes that we need, the growth of data centers is dramatically faster than the growth of production of green hydrogen. We can't wait for the green hydrogen to be ready because we're going to get data centers which are dirty at this point from a carbon footprint perspective, and it will stay with us for the next 25 years. So we have an opportunity right now that comes every 20 to 25 years in a very fast hockey stick growth in data centers. The more data centers we'll put that are going to be zero emission from the fence in, the better we are for the next 20 years, because the next 20 years will bring more and more green hydrogen, more and more sophisticated blue hydrogen, etc., and pushing the natural gas into the data center is the wrong way to do it, because there's no way to actually back away from that. And we create a problem that will not be solved.
Yeah. Let's talk a little bit about the cost, because that will also influence adoption as well. And the U.S. National Clean Hydrogen Strategy and Roadmap that they released, at least I saw a document from June 2023, they're talking about a target hydrogen production cost of $1 per kilogram by 2031 and a delivery and dispensing cost of $2 per kilogram by 2030. So that's about $3,000 per metric ton by 2030, roughly. How does that compare to the cost of grid electricity today?
Exactly. So when you can reach $1 per kilogram in cost, you can extract out of that energy at about 4 to 5 cents per kilowatt hour. So if you're in that place, you are better than most places in the world, and dramatically better from places which have high cost of energy. In California, for example, when you try to actually get a new lease, not a grandfather lease, you're going to get between 30 and 32 cents per kilowatt hour, maybe 28 if you're a very large consumer. In Germany, the price is 45 to 50 cents per kilowatt hour. So if you bring a 4 to 5, that's amazing. Now, if you talk about the transportation and liquefaction of the hydrogen, because we need to liquefy to transport it, that's an additional $2 per kilogram, and that puts us at about $2.5 to $3 per kilogram of hydrogen, which means that we're going to be around the area of 17 to 18 cents per kilowatt hour to produce the energy. That is still attractive in a lot of places and beats the grid connection energy. And this is only for smaller sites. So you are not going to be delivering hydrogen to larger sites. Yes. So if you need a specific data centers closer to the center of the city or closer to a factory, and you can do delivery, it's okay to pay 18 cents per kilowatt hour. So I think the pricing targets that they have are very aggressive. And if we can achieve them, we'll be actually generating energy at a lower cost than what we have right now. We even now, at our site in Texas, can deliver to our customers energy at a lower cost than what we will get if they connect to the grid over there. And then we also can give them what's called, there's no word in English, called descalator. We just invented it. And that's reducing the price of energy with time. Because the more energy we produce, the more hydrogen we use, the lower price we pay for the hydrogen because our volume discounts kicks in. So the larger the site is, the lower the price of energy is. Our customers are shocked that we can offer to them a reduction in price of energy over time, but we can because that's the way the contract works. You consume more, you pay less. We have not seen a drop in our energy cost for a very long time. So this is an interesting phenomena that comes with the hydrogen use for generation of energy.
And I do see hyperscalers, though, announcing exploration of other technologies like nuclear power. Some are looking at biofuels and, of course, wind and solar coupled with large battery storage as alternatives to grid power. What is your sense of their interest in hydrogen power as an option? Is cost the main thing, or are there other kind of things you think they're concerned about?
So I think if you try to look at alternative solutions to the hydrogen solution, so let's start with nuclear. So nuclear is today emerging, and I think it's the new shiny thing that everybody looks at. But nuclear will not go into production until the end of the decade. And even then, it has a lot of challenges to overcome. Like, nobody wants a nuclear plant in the backyard, and you're going to have a more complex process to actually bring it in. But it's definitely an alternative that will come in the next 7 to 10 years. And each one of the hyperscalers needs to actually see if it makes sense for them to make investment towards that. The alternative of solar, wind, and battery is much, much more expensive than hydrogen. So it's creating for you a very, very expensive solution. It is available, but again, not at scale right now. And the limiting factor is the number of batteries you can put to actually maintain 24/7, 365, and the length of the time that you could expect to have cloud cover. If you have cloud cover for 2 weeks, what happens? You need to actually store energy for 2 weeks to be able to actually to maintain this. That's a very, very challenging thing. It's not just for every 24 hours I need to store for 18 hours. Suddenly I need to store for 18 weeks or 18 days. And then it's a problem. And that's also not applicable everywhere, right? So if you go, for example, to areas which are more on the north side, they have much less sun. And they might have a little bit more wind, but they have much less sun. And as a result, it's less of an alternative. We need bigger and bigger sets of batteries. They're very expensive, and they're not available at the volumes that we need. Hydrogen delivers a solution now, not 5 years, 7 years, 10 years out. And they give you a solution that's implementable without creating something which is a crazy technology invention. We did not invent cold fusion over here to actually make our data center sustainable. We took hydrogen, which was available in the market. We took fuel cells, which are available in the market. We repurposed them and redesigned the system around them to work for the 24/7, 365 requirement for the data center. But there's nothing over here which was, we reinvented the energy sources for the face of the earth. We didn't have to do that. It was available. We're continuing to develop and make the fuel cells better and better hydrogen, etc. But it's based on more or less technologies that have been discovered many years ago and been used in different applications, and we just repurpose it for the data center. And that's the beauty of it. It's here and now. So I was part of a discussion about energy availability and energy availability on the grid. Yeah. And some of the people were saying, okay, we'll solve the problem in 2035. And my view on this is we won't have that problem in 2035. We have the problem right now. In 2035, we don't know what's going to be the demand, what's going to be the growth, etc. It's 10 years out. And we need to solve the problem now. And right now, there are not a lot of ways to solve this problem. And hydrogen is probably one of the primary one, both for sustainability and availability.
And kind of a side topic, I don't know if you touched on it earlier or not, but it's the buildings themselves. You 3D print buildings for your data centers. Is this again to deal with the modularity and the speed aspect? Is that the advantage of doing that?
Yeah, so 3D printing has multiple aspects to it. One is, like you said, it costs much less and it's much faster. We can print in about 25 hours a megawatt of data center. And the other aspect of it is 3D printing is the most sustainable construction methods because it's a waste-free and litter-free solution. You bring the materials, you put it into the printer, you print it, and then you just remove the printer. Nothing comes out of the site. So, and it gives you also the option to select different kinds of cements to use. You can use renewable cement, you can do green cement. There's a lot of technologies around cement right now, and it gives you the availability to create variable solution. So it's time to delivery, it's the cost to print, which is much faster, and it's associated with the modularity because you cannot 3D print very large structures. But because our modular blocks are small, 1,000 square feet, then we can 3D print them and get all those benefits without risking anything and reducing our cost to build dramatically.
That's Yuval Bachar, who is the founder and CEO of Edge Cloud Link, based in Mountain View, California. And my sincere thanks to Yuval for taking the time to share his insights with us on Perspectives with Nilo. We've placed links to ECL's website, as well as to the US National Clean Hydrogen Strategy and Roadmap, and lots more related information in the Dive Deeper section of our blog, which you can find at pwnilo.com. There, you'll also find links to our social media and past episodes, so be sure to give us a like or subscribe. We'd really appreciate it. And that's where we leave it for the moment. As always, thank you for listening, and until the next time, bye for now.